many ML AI experts and enthusiasts here on a Friday night. So yeah, let me get started. So my talk is going to be about defect detection. And so what is a defect? So working at one of the world's largest retailers, Amazon ships millions of products every day. And customers expect products to arrive in a perfect condition. And a defect is something that makes a product unusable, or that doesn't turn into a pleasant customer experience. And so the goal of this talk is to convince you that actually visual detection of defects is a really hard problem. And I'm going to share with you what we are doing to engage with the community to drive innovation that will hopefully ultimately benefit everyone in the quality inspection space. So more concretely, I'll be talking about two things today. So I'll be talking about the Kaputt dataset, which we released last year and presented at the International Conference on Computer Vision, ICCV. And then, I'll invite you to help us solve this problem by pitching the Visual Anomaly and Novelty Detection Challenge, which is co-located with the Visual Anomaly and Novelty Detection Workshop at CVPR. And so why should you do that? Well, maybe you're an idealist and you really care about AI. Well, but we also have some prize money. So a pretty good amount of prizes worth more than $25,000 US. I'll talk more about this later. Okay, before I dive into it, maybe some details about me. So I want to just quickly introduce myself. So I'm Sebastian. I'm a manager of applied science at Amazon for Fulfillment Technologies and Robotics. And I heard that I'm like a bit of a rare creature because I'm an actual Berliner, so born and raised. Even though you'll see like my career path took a bit of a curiosity-driven winding path, I completely fulfill one important cliche about Berliners. So what cliches do people know about Berliners? So raise your hand. I'm curious. Yeah.
Black clothing.
Black clothing. Okay, almost. Yeah. Okay, good. I fulfill that one. That's not the one I mean, though. Anything else?
Beer drinker.
Beer drinking later. Also good. Yeah. Okay, we're also. Yeah. Sorry. Techno. Okay. No, not my thing. Okay. Being extremely unfriendly, I hope I'm not coming across as that. We can chat later and then you can tell me. No, but I mean, Berliners, it's said that Berliners never leave their city, and you will see on except for a couple of weeks of vacation, and so you'll see that when I tell a little bit more about myself. Anyway, so after doing stuff in Berlin, I studied computer science, got my master's degree at Humboldt University, and did some explorations in the startup world back then. The internet was still new and cool, and after some successes and some big failures, I decided to go into academia, received my PhD at the Robotics and Biology Lab at TU Berlin. And why am I telling you all of this? Because I'm talking about a challenge and kind of pitching a challenge here, and kind of wanted to give this personal spin how actually participating in challenge gave quite an important nudge to my career. And so I was really interested in robotics, and more precise robotic manipulation, grasping, and these kinds of things. And in 2015, my team, my lab at the university, we participated in an inaugural challenge that was held by Amazon, the Amazon Picking Challenge. And the goal was to build a robot that could fulfill a simulated order, by picking, detecting items in a warehouse shelf, picking them up, and putting them into a bin. And this, our robot was terribly slow. The problem was way simpler than what the actual problem is. But due to some good engineering, science, and a fair amount of luck, we managed to win that challenge. And a leap forward, one thing came to another, and in 2017 I joined Amazon as an applied scientist. There was the idea of establishing a robotics R&D unit, and was very lucky to be a founding member of this unit. And then 2021, after doing some robotics, I switched to computer vision, and in 22 became a manager. I'm going to talk to you a little bit about, in the next couple of minutes, what my team has been doing. What's next? Well, obviously, a lot of stuff, and agents are a very important and interesting thing. Luckily, I now know how to fix them. Thank you, Bilge. So that will be probably my next talk next year, how we managed to do this. Okay, enough about me. So what is visual defect detection? Where are we coming from? So traditionally, the field has mostly focused on what I would say industrial manufacturing applications of defect detection. And so defect detection, goes under a lot of names. You will hear the term anomaly detection, novelty detection. It's all, like it has all its nuances, but it's kind of, for the sake of this talk, it's all the same thing. And like a really seminal data set was the MVTech AD data set, which kind of really put the visual defect detection challenge out there for the community to solve. And like the setting is as follows. So like you have, for example, you're manufacturing, for example, these kinds of pills, if you look at the third column, and then you have a lot of images of these pills, always in the nicely aligned, in the same lighting, in the same situation, in the same pose. But the problem is you don't have data, or very, very few data, of what these items look like when they're defective. And so the challenge is, so basically, can you, see my screen? So basically this is like an undefective example, and then you have a lot of these, and then you need to see, for example, there's a little scratch here, I think, on the pill, and need to be able to detect this. And then, a couple of other data sets followed, like the Visa data set. And the community did an amazing work and like really pushed the state of the art forward. So some of the best methods reach way beyond 94% OROC. And then, we started working on it from the retail perspective, tried some of these methods, and well, first of all, realized the state of the art benchmark, they're saturated, right? Basically the methods, they're at 99% now, and there's not much to gain from doing these, doing research on these data sets really. And the second thing, actually the methods that we then saw there and we tried them on our task, they didn't work. And I want to explain to you why they didn't work in the next couple of slides. So what makes the visual defect detection in retail and logistics particularly difficult? And so you already saw I want to make this interactive, so I want to play a game. So the first question is, please raise a hand if you're seeing a defect on this image. Yeah, some people are still digesting the coffee break. So I see a couple of hands. It's a pretty obvious example. Maybe also the lighting is not great here, but you see there's this spill, so this detergent basically spilled into this container. So it was the easy question. Okay, now we come to the actual tricky bit. Okay, what about this example? And I realize it may be hard to see on this screen here. Maybe someone can see it. Sorry? Label damage? No. I think it's really hard to see. I'm going to tell you what is not the problem. So the problem is not that there's kind of this dirt on the container. So it's actually pretty common that you have like leftover stuff in the container. It's been cleaned, but it has this kind of noise that the model actually needs to detect, actually needs to ignore. So that's not the problem. But the problem is, and you still cannot see it, but actually there is a crease here. So the cover is creased. And so this is a really subtle defect that, as we saw, it's actually really hard to see, especially if your lighting of your presentation is bad. Okay, maybe let's take another one. I think this one should be visible. It's one of my favorite examples. So who spots the damage? Yes? Yeah, exactly. So you see here that the detergent has spilled, but the interesting bit is there's actually no sign of a hole or a penetration or a tear, right? So the model needs to decide, needs to kind of understand something, that this is detergent, that this is what detergent looks like when it spills, even though there's like no visible hole or something like that. So we call it something like a logical defect, because it could also be just some leftover dirt that actually doesn't really matter, right? Like in the previous example. Okay, another one. Any guesses? Okay, so there is actually no defect on here, but you could think that, oh, sorry, did I not show this image before? Oh, sorry, okay. So you could think that there is like a hole in this book and the monster is peeking through it, but this is obviously just the cover of the book, right? So we know that, but a vision model might not necessarily understand that, because this looks exactly like one of the holes you would see on a package, right? And so we call these adversarial examples, and I have a whole collection of these, having been at Amazon for a while. So you could say, you know what, but we do know what this book usually looks like, right? So why can't we just compare it? And fair point. So we can use something we call reference images, and we can look what previous instances of the same book that we sold to customers look like. And now there's a bit of a problem here. Namely, we have no control over the post. So different from the manufacturing use case, we cannot even guarantee it lands on the same side. And also we have rotation, and this is actually an assumption that many of the methods that were proposed for these manufacturing use cases actually exploited. Well, and so then there's the biggest problem. If you have manufacturing use case, usually you're producing a couple of products, right? You have maybe 2 types of toothbrushes, and these, always look exactly the same. But if you're selling pretty much anything that's out there, you can buy on the internet, and the product variability and the variability of what these defects look like really hit you. Okay, so I hope that you're all now very sad, and because this is such a difficult problem, but I think that, now I hope also motivated you to help solve this. So, visual deforestation, I think, is a difficult problem. Retail logistics comes with its own challenges, and now the question is, can we as a community solve it? And now I want to tell you what we did, to kind of drive this. So the first thing I'm going to introduce briefly is the Kaputt dataset. For all non-Germans, Kaputt is the German word for broken, so kudos to my colleague Dorian who came up with the name. So I'm going to talk about this, and then I'm going to talk about the challenge that is happening right now. Okay, so let's get started. So some stats. So Kaputt has over 230,000 samples, so images. Out of these, 100,000 are labeled with damage severity and damage type or defect type score labels. And it has a really huge number of defective samples, more than 29K. And it also reflects the huge variability in products by having 48,000 or more than 48,000 unique products. And so basically when we released it was 40 times larger than these state-of-the-art data sets that I was talking about before, and it's also from a different domain because it's from this kind of retail logistics domain. So really quickly about the structure, so you can already prepare yourself mentally what you have to do when you participate in the challenge later. Every sample comes with an image plus an item identifier. It's just like a hash that uniquely identifies the item, because we may have a couple of images of the same item in the data set. Then we have a defect severity label. It can be no defect, minor defect, or major defect, which we collected manual labels for. And then also a defect type label, which I showed you before. We have spillages, opens, or deconstructions where things fall out of a box, and we have a label for that as well. And so, and additionally associated with every of these samples, we have up to 3 reference images, as I showed you in the book example, and these can be assumed to be non-defective, but are not guaranteed to be non-effective. So this is also reality. Everyone who works with data knows it's really hard to get clean data, and this is the reality that sometimes your data is not clean. Okay, so when we submitted this to ICCV, obviously we needed to make a point that this is really a challenging task, right? That we're not just making this up. And so we tried a whole bunch of different baselines. You will find more in the paper, and I want to highlight some of the key results. So the first thing is that when you try some very naive supervised learning, actually this works really well. So we just took the samples, we actually ignored the reference images, and just threw your favorite methods, vision transformers, ResNets, edit. And with the vision transformer got more than 90% average precision or 94% area under the ROC curve. So great, right? Problem is solved. We said, oh, maybe it works even better if you throw reference images at it. Turns out we didn't get that to work, the model couldn't really figure out how to use these, so definitely an opportunity to do it. So we're done, right? Okay, now because I still have a couple of minutes. So the problem with that is that this is not a realistic setting. This was trained on 29,000 samples of defective items, right? Which is absolutely unrealistic in practice. In most practical settings, unless you really screwed up setting up your manufacturing or a retail pipeline, you have very, very few defects. It's an absolutely rare event, which is great for your customers, but great for you, really stupid for you as an ML researcher who wants to build model and run supervised learning, right? So that doesn't fly. If we need better methods that can actually deal with less data, especially of damages and defective samples. So we proved that. We basically reduced to some little bit more realistic defect rate. So here we just have less than 1% of all the samples in the data set are defective. And then basically our performance drops significantly to only 57% average precision. And even 1% is way higher than what you want your defect rate to be. That would get you in big trouble. Okay, so then also like the Geminis and Chat and GPTs of this world, you know, the question is how well do they do? And we tried, tweak the prompts and tried this, and actually it worked not so great. We were surprised that the models really struggled to, reliably detect defects, and in some cases they're like amazing. They describe like every detail of the product and the defect they see. In some cases you have a spill, like the one with the detergent, and they just say, oh, this is in perfectly pristine condition. So clearly these models have been trained on a lot of data that involve objects, everyday objects, but not these kinds of, whenever you go to some niche application, the models start struggling. And I'm not a very good prompt engineer, so maybe we also just screwed up, and you can prove me wrong, and maybe that's not right. And these models are actually much better than we think. Okay. That's it about the Kaputt dataset. If you want to learn more, there are much more details in the paper. You just go to www.kaputt-dataset.com, and there's also a QR code here. And there will be another QR code at the end of the slides. Okay, so let us then talk a little bit about how you can help solving this. So I'm very excited that for the first time I am co-hosting the Visual Anomaly and Novelty Detection Challenge. I've been invited by the main organizers. So some history, so this challenge, VANT, as the abbreviation, has actually been happening for a couple of years now. This is the 4th edition, always co-located with a very exciting workshop at CVPR. And we have an amazing team of organizers. We have MVTech, who released the seminal data sets and are like some of the leaders in this space. Paula, maybe some of you know it, especially the Voxel 51 people, very involved in this. And then a couple of people from my team, and then two really great people from Intel AI as well. And then altogether, these sponsors chipped in to come up with a really nice price package. So we will have prices worth more than 25K. Like it will be cash prizes, but also some really cool Intel hardware and some other gimmicks that you can win. I'm going to tell you in a minute how exactly to do that. So the challenge is still on. It started on April 1st, but you can participate at any time. So if you just navigate to the challenge page, I'll tell you a bit of high level how it works. There you find the complete rules, and you have time to submit your solutions until May 14th. So I think it's another 4 or 5 weeks actually. And the winners will not only get prizes, but they will also be invited to present their solution as a short video at the workshop at CVPR in 2026 in June. Okay, so a bit more details about what this challenge looks like. So we have 2 tracks. There's the industrial track and the retail track. And so the industrial track is based on a new version of this MVTech AD dataset. And here the challenge, is actually becoming a bit more difficult. Like there are a lot of, variations in lighting and so that you now need to solve here. But also it's actually not only about detection, like in the retail track, but it's also about segmentation. So one of the key tasks is that you actually need to not only say that there's a defect, but identify and localize the defect. And then there's the retail track, which looks pretty much exactly the same like the Kaputt dataset. We have a Kaputt 2 dataset, which is a pure test dataset where we're not publishing the labels, and you run your model locally and then submit your predictions on the submission platform, and then get a score back, and then we will see who does the best. That's not the only thing. We actually have a couple of different categories. So we have best overall performance. This is just based on a track-specific metric. But then also we have a zero-shot off-the-shelf prize, an efficiency prize, and a best paper prize, which I'll briefly talk about now. Oh, and the runner-up also gets a prize. Okay, so best overall performance. We have $3,000 cash prize for this, and $750 for the runner-up. I'm not going to bore you with the details of the metrics. You can see it on the website. It's going to be like a segmentation-based metric for the industrial track and based an average precision, exactly how, like in the Kaputt paper. So instead of boring you with details, I'm just going to show you a mean. And if you're like a Kegler or like really skilled model tweaker, I think this is for you. So then I think this is a really cool challenge, the zero shot and off the shelf challenge, which is actually worth like exactly the same price money. It's like $3,000. In the industrial track, the challenge there is around zero shot, so you're not allowed to use any images of the MVTech AD2 data set. So this is important because these images, in the industrial setting, as explained before, show you like what the items look like in their undamaged, undefective state. And the question is, can you do without? And in the retail track, we're actually interested in, can you take off-the-shelf vision language models and make them work really well without any weight or architecture modifications? So again, here's the meme for you. So if you're like an amazing prompt engineer, then this challenge is definitely for you. Okay, and then we have a completely orthogonal price, not completely, but kind of, which is about efficiency. So one thing that I haven't talked about at all, that in industrial settings, you cannot always just throw a 32 billion parameter model at your problem, right? Because you may have constraints. You may have constraints around your edge compute where you need to deploy it. You may have constraints around the latency and what amount of time you have for your model to make a decision to actually have a meaningful impact on the process where you're integrating it. And so this award talks about measures power consumption, memory footprint, inference throughput, and also obviously takes performance into account to then see which of the models are actually in a practical sense most usable for industrial use cases. And of course, here's your meme about efficiency. Okay, and the final prize, and this is a serious prize, so there will be no meme, is about the best paper. Because, challenges are great, and being the best on a leaderboard is great, but we all know true innovation sometimes comes from trying out crazy ideas that nobody has thought about, and that may not work as well initially, but that really spark, ideas and an interest. So we also decided to award this. Everyone who participates needs to submit a technical report, and then a jury will judge the innovation, efficiency, generalizability, and explainability capabilities of the technical reports and models proposed. Okay, so I'm almost at the end. To summarize, I hope I convinced you that visual defect detection is a really difficult and interesting problem, and to join the Vent 4.0 challenge to help solve it. These are all the details about the challenges, the challenge, and here you find QR codes if you want to learn more about the Kaputt dataset and the details of the challenge, and I'm happy to take questions.